In this video, we're going to take a look at binomial distributions. So last time we looked at representing unknown potential outcomes using random variables like x, right? This time we're going to look at a special random variable, one where we look at the number of successes in n trials. So let's start with a quick example, bringing back some of the other things that we have looked at recently. So we have 500 candies in a jar with 40 of those being blue, and we're going to draw 2 candies in a row, replacing and mixing between pulls. What is the probability of drawing 2 blues? And if you do not replace a candy between 2 pulls, what is the probability of drawing 2 blues? All right, so let's take a look at the with replacement case first. With replacement. And in that case, we want to show with a tree what our possible outcomes were. And we can start by getting a blue candy, or we could get a not blue candy. That's your first selection. Then we go to get the other selection. And again, we could either get a blue candy or we could get a not blue candy. And that's true for either of our outcomes from the first selection. Now we need to put in the probabilities on this. And our first selection, we had 40 that were blue. So 40 out of 500 are blue and not blue. The remaining of the 500, right, because we need to add to 1, that's going to be 460 out of 500 are not blue. Now we're going to replace it, right? So we draw that candy, then we put it right back in. That means we haven't changed the probability at all. It's still going to be 40 out of 500 are blue, 460 out of 500 are not blue. So we can just replace that up here, 40 out of 500, 460 out of 500, 40 out of 500, and 460 out of 500. Okay, now if we go to the without replacement option, without replacement, this means that when we select our first candy, we're going to keep it. We may eat it, right? It's going to go away somehow from our collection of remaining candies. And so that means our probability will change when we look at the second selection. So the first selection still is going to be blue and not blue. Okay. And then our second one is, going to be blue, or we'll have not blue. So we'll do the complement, blue, and we'll have not blue. So either version of the not blue or the complement notation works just fine here. And then we're going to have for our first selection, still 40 out of 500 are blue, 460 out of 500 are not blue. But then once we take one of those, so make that selection of a blue candy, we're going to keep it. So that means there's only 39 out of 499 left. And of the not blue, there were still 460, but out of 499. Likewise, we're going to take a not blue candy out of the mix. That's still going to leave us with 40 blue, but out of 499 total, and 459 not blue out of 499. And those should add to 1. So we see then that we have a change in probability as we go from one step to the next. So our likelihood of getting a blue candy is going to be changing depending on whether we have drawn a candy and replaced versus drawing a candy without replacement. And so in this case, since we see that those probabilities are equal, we would say that the with replacement case is independent, and our without replacement situation is dependent. We have a change in probability. Dependent. Now those probabilities aren't hugely different though. So if we look at what 40 out of 500 is, that is 0.8 or 0.08, sorry, missing a 0. And if we look at what 39 out of 499 is, it is 0.07816. So just a slight difference in probability. We have not seen a huge change by taking that one candy out from 500. And that's also true for our calculation of the and probability. So if we're finding the probability of blue and blue, like the question was asking, that would be 40 out of 500 times 40 out of 500. Since we are drawing with replacement in this case, probability is not changing. That comes to 0.0064. And if we did the same calculation without replacement, the probability of blue and blue is going to be the 40 out of 500 times 39 out of 499, and that's going to be 0.0095. So if we rounded to the nearest whole number, to the nearest whole percentage, so to 2 decimal places, these would both end up being the same. So again, we're not seeing a huge difference in our probabilities based on the difference between independence and dependence when we're drawing a small number of things from a larger group of things. And that's ultimately what we're wanting to be able to have happen. We want to be able to assume things are close to being independent, because then it gives us a lot more freedom in doing our calculations. If we can kind of assume close enough and use the same probability through all of our branches, it makes thinking of what the calculation would be a whole heck of a lot easier. And that's what we're going to refer to here as pseudo-independence. So ultimately, independence, when we say things are independent, what we mean is that the probability of one thing is not affected or changed by the occurrence of another. Or if we look out of different groups, we're not going to see a difference in their probabilities. So as seen in the previous example, when we draw without replacement, we technically change the probability and therefore events are not independent. However, if we're drawing from a large enough population, the change in probability is small enough that we can assume events are at least pseudo-independent. And as a rule of thumb, we can assume independence and use those easier calculations provided the size of our sample is less than 10% of the population. So let's run through a couple of checks here for pseudo-independence. And so let's say we sample 10 times without replacement from a population of 10,000. Can we assume independence? By that we mean pseudo-independence, right? Pseudo-independence. We know if we're drawing from a fixed population without replacement, it's not going to be truly independent. But is the difference small enough that we can assume pseudo-independence? All right, so we know that N, our sample size is 10, and our population size, uppercase N, is 10,000. And we can calculate 10% of 10,000, so 10% of 10,000, which we would calculate numerically as 0.1. So change the percent to a decimal times 10,000, and that's equal to 1,000. So that is 10% of 10,000 is quite a bit larger than N. So that means N equal to 10 is less than 10% of 10,000. So we can assume independence. It is pseudo-independent. Okay. And how about another one? We sample 40 times without replacement from a population of 200. Can we assume independence? So in this case, N, our sample size is 40, and our population, uppercase N, is 200. We want to check 10% of our population size, so 10% of 200, so 0.1 times 200, and that is equal to 20. Okay, so now N equals 40 is actually greater than 10% of the population. So it's greater than 10% of the population. So we cannot assume independence. Okay. In that case, we're drawing too many from a small population size, and so those changes in probability are going to be too significant to just overlook. We can't just let it go. Okay, so the next step in getting to where we ultimately want to be in this note packet is to look at Bernoulli trials. So our goal is to determine the probability of case successes in N trials with order mattering, but we're going to start small. So we're going to look at the probability of one success in one trial. All right, so for example, we're going to flip a coin, a fair coin once, and we're going to let X represent the number of heads. We want to get the probability that X is equal to 0, so the number of heads is 0, and the probability that X equals 1, which is getting 1 head, and then find the expected value, the variance, and the standard deviation for that. All right, so let's run through that process. To come up with the probabilities, it's always a good idea to just think of the tree. So we could get a heads or we could get a tails. And this is representing the real life situation, right? And then we know that the probability for a fair coin should be 50-50 for each of those outcomes. And that means that our probability of getting a heads, so X being equal to 1, is going to be equal to 0.5, and the probability that X is equal to 0, so having tails, no heads, is going to be equal to 0.5. This then will allow us to create a probability distribution, so knowing what the possible outcomes are and the probabilities of each of those outcomes. We could have 0 or 1 heads, and each of these has a probability of 0.5. Expected value is how many heads on average we could expect over the long run, were we to repeat this flip of the coin over and over and over again. Okay, so that means we're going to calculate that as each outcome times its probability. So 1 times 0.5, and so then we get 0.5 heads, as we should expect, right? If we're only flipping it once, we could get heads or tails equally. We would expect over the long run for those to balance out and on average get half a head, if you will. All right, and then the variance of X is what we find before getting to the standard deviation, and that's going to be each outcome minus the expected value squared times the probability of that outcome plus outcome minus the expected value squared times the probability of that outcome. Okay, so we're going to get 0.5 times 0.5 plus 0.5 times 0.5, so that is going to be the 0.25, and that is heads squared, since we were squaring those quantities. Okay, and then we've got the standard deviation of X, and that is going to be the square root of the 0.25, which brings us back to 0.5 heads in its regular units, not squared anymore. So together, this is saying that we can expect to get half a head, give or take half a head. So somewhere between 0 and 1 heads. Haha, kind of what we already knew. Okay, but that's the general properties of what we've done so far to do calculations with trees and coming up with our random variable possibilities. Okay, now let's define this Bernoulli trial. So if we call a random variable a Bernoulli trial, that means there is a fixed probability of success and failure. So we call the probability of success, we give the symbol P, and let's say it was 0.3, then the probability of failure we name Q, and it's equal to 1 minus the probability of success. So in this case, it would be minus 0.3, which would be 0.7. Now notice these are just complementary pairs because we can only have 2 possibilities, either success or failure. So our probabilities must be complements since we only have 2 possible outcomes. The other thing we need to call a random variable a Bernoulli trial is we need to be able to assume independence, okay? So this could either be a natural independence, so natural independence, or pseudo-independence. Pseudo-independence. Okay. Natural independence are these situations like coin flips, dice rolls, pregnancies, where there isn't a fixed population that we are drawing out of. Okay. So in those cases, we just kind of examine the situation and think, okay, well, is it likely that we're going to see a change in probability based on something happening? So in the terms of coin flips, there's no change in the likelihood of getting tails just because you've already flipped tails, for instance. Die rolls. There's no change in the likelihood of rolling a 6 just because you happen to have rolled a 6 already. Okay, so that's those natural independence cases. Pseudo-independence is when we're drawing from a fixed sized population. So drawing a sample from a population of people, let's say for social science experiments and surveys, then we know that we have a fixed endpoint. We've drawn one out. Technically speaking, they're not independent, but we can assume pseudo-independence if we meet that 10% rule, or if n is less than 10% of the population. Okay. So if X happens to be a Bernoulli trial, then we actually get some pretty cool information. We can go back to our previous example to verify that. So if X is Bernoulli, then that means the expected value of X is going to be equal to P, the probability of success. Well, that actually is true up here. Our expected value was the probability of success. It was 0.5. Okay, how about the variance of X? Well, the variance of X, P times Q, that was 0.5 times 0.5, which was 0.25. Aha. Yes, indeed, that works there too, right? So this is equal to P times Q. This is equal to P, which means then the standard deviation of X is going to be the square root of P times Q, so times 0.5, which is going to come back to being just 0.5. So these things are actually kind of handy to know, right? We don't have to go through big calculations, or at least in this one step, and hopefully with more steps. Okay. So let's suppose X is a Bernoulli trial and P equals 0.2. Remembering P, this is the probability of success. And we want to calculate the expected value of X, the variance of X, and the standard deviation of X. Well, if the probability of success, P, is equal to 0.2, then that means the probability of failure, Q, will be 1 minus 0.2 or 0.8, since they're complementary pairs. All right. Because we got that X is a Bernoulli trial. So that means we know that there is a fixed P, and that's going to be equal to 0.2. We know that we have only success or failure, and we know we have independence. Right, either naturally or pseudo-independence, one of those three. Okay, so we know we have those, and so now we want to find E of X, remembering that that is just going to be equal to P, so that's going to be equal to 0.2. We know that the variance of X, that is equal to P times Q, so that is going to be equal to 0.2 times 0.8, which is equal to 0.16. And in this case, I'm going to add just the label units for my unknown units. In a context, we should know what those units are, but we can go ahead with this. And then we know that we can get to the standard deviation of X is going to be the square root of 0.16, which if we take a look at that, that should be 0.4. So square root of 0.16 is in fact 0.4, and we're back to units again. All right, so the binomial random variable is just an extension of this. So instead of just looking at a single case, we're going to look at multiple trials, or n being greater than 1. So we call a random variable a binomial random variable if there's still this fixed probability of success and a fixed probability of failure, so P and Q. We still need to have two options per trial, so a success and failure option, and we can still assume independence between trials, either pseudo or natural independence. And the thing that we add to this is that we need to have a fixed number of trials. So these first three conditions, this is just Bernoulli, right? And then we're adding this to make it binomial. Okay, so a binomial distribution or a binomial random variable is one that's made up of Bernoulli trials and to a fixed number of trials. Okay, So we define the binomial distribution as x equals b with an n and p being defined, where n is the number of trials and p is the fixed probability of success. X is the number of successes in n trials. So if you're ever asked to define the binomial distribution, what that means is to give the label x, set it equal to the b, which means binomial, and then give the value of the number of trials or sample size and the probability of success p. All right, so let's take a look at another example. In a particular family, there's a 30% chance that any child has brown hair, and the family has 3 children. We're going to let x represent the number of children with brown hair. So is x binomial? So the first thing we're going to need to do is come up with our rules. So what do we need to be true in order for this variable to be a binomial random variable? And we can basically just bullet point this off. We need to have a constant probability of success. So constant probability of success. And in this case, we do. There is a 30% chance that any child has brown hair. So p is equal to 0.3. The other thing that we need to verify is that there's only 2 options per trial. So only success or failure. And in this case, that is true. They could have brown hair or not brown hair. Those are our only 2 possibilities. The other thing we need to check is that we have independence. Okay, so there are 3 children, but this is again not of a fixed number of children possible. So this is more of a natural independence situation because we're not drawing from a population. So we'll say this is naturally independent. Okay, so whether or not you have 1 kid with brown hair does not change the probability that your next child is going to have brown hair. And then the last thing we need to check is whether or not we have a fixed number of trials or a fixed sample size. So fixed number of trials, and that is true since n is equal to, well, we're going to go through 3 children. So n is equal to 3. So given we've got these 4 conditions met, yes, x is binomial. Now, the other thing we always want to double check as well is what is the purpose, like what's being measured by this variable? So in addition to having these 4 things being met, we're also looking for number of successes in n unknowns or n trials, trials. So yes, we're looking for the number of children with brown hair among the 3 children. So yes, that basic setup is binomial, and we have all of those 4 conditions met. So yes, x is going to be binomial. And we can define that as well, right? So this we would define as being x is our thing that's being distributed. And then we set it equal to b, meaning it's a binomial distribution, and we have n is equal to 3, and the probability of success is 0.3. So this is how we would define the distribution. Okay, oops, there we go. All right. Consider the family with 3 children. Sketch a tree diagram illustrating the possible hair color outcomes. All right, so we have 3 children. They could either have brown hair or not brown hair. That would be the first child. Then the second child could have brown hair or not brown hair. Brown hair, not brown hair. And then you have the third child, brown hair, not brown hair, brown hair, not brown hair, brown hair, not brown hair, brown hair, and not brown hair. Okay, so there's our tree with the possible outcomes. Let's add the probabilities. There's a 30% chance of having brown hair. So this would be brown, not brown is then 70% or 0.7, because remember this is P. That makes this Q, which was 1 minus the probability of P. All right, and then since we've assumed independence, okay, naturally independent situation, the probability of having brown hair is not going to change. So we still have 0.3, 0.7, 0.3, 0.7, 0.3, 0.7 on all of these branch segments. 0.3, 0.7. Okay, now we want to create a probability distribution for X equaling the number of children with brown hair. So it's going to be helpful to go back to our tree and figure out, well, what were the values of X for each of these branches? So in this case, all 3 children had brown hair. So X is equal to 3, then X is equal to 2, X is equal to 2, X is equal to 1, X is equal to 2 again, then X is equal to 1, X is equal to 1, X is equal to 0. So none of the 3 children had brown hair in that last branch. Okay, so now we know that we have our possible outcomes for X, and then the probability for X equaling X. All right, so we could have 0 with brown hair, 1 with brown hair, 2 with brown hair, or 3 with brown hair. All right, so those. Now the extreme cases, remember, are pretty easy because they're only happening on one of those branches. So to have no one with brown hair, it's happening in that bottom case, and so that's just the 0.7 times itself 3 times. So 0.7 times 0.7 times 0.7, and that's 0.3430. So I'll move that over so it's not quite so cramped. 0.3430. And all of the kids having brown hair, that's going to be the other extreme, right? So 0.3, the success probability for each and every one of those segments, so to the third power, and that's going to be 0.0270. The 1 and 2 cases, this is happening on 3 of those branches, so we need to take the sum of the probabilities of each of those branches. And we look at it, though, to have 2 successes, 2 kids with brown hair, each of those segments would need to have had a probability of 0.3, and then the 1 failure would be a 0.7. Or if we had 1 child with brown hair, each of those branches where that occurred, we're going to have 1.3 and 2.7s. And it doesn't really matter the order when we're doing the calculation of the product. So these will be 3 being the number of branches where we had 1 child with brown hair times the probabilities along those branch segments, which is going to be 1 success and 2 failure, so the 0.7 squared, and that's going to be 0.4410. And then having 2 kids with brown hair, that's also happening on 3 of those branches, and in order for that to have happened, we needed 2 successes, so 2 of those 0.3s and 1.7. And then that's going to come to 0.1890. And again, this is a probability distribution, so those probabilities should sum to 1, which they do, but double check it as part of your work. And then we're going to want to follow up with some probabilities. Now, later on, we'll also want to get to the expected value and all those other things. And remember, expected value, how far on average, right? We're going to be expecting to deviate from the mean, or in the expected value for these probability distributions, what should we be expecting over the long run as an average for this? And we look at the probabilities for each of these outcomes, we see that the most likely scenario is a 1, a little bit of pull over to the 0. So we're expecting probably a probability or the number of children with brown hair to be somewhere between 0 and 1 out of those 3. Okay, that's likely what we would get as an expected value based on kind of histogram image that we get from it. All right. But we want to know what is the probability of getting at least one child who has brown hair. So the probability that X is at least 1, so 1 or more, so greater than or equal to 1, is going to be the sum of the probability of 1 plus 2 plus 3, or we can do 1 minus the probability that X equals 0, which is usually a much quicker process. So 1 minus 0.3430. And that's going to be equal to 0.6570. Now, alternatively, again, you could say that this was the sum of probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3, and those would be equivalent. All right, what is the probability that at most 1? So at most 1 is going to be 0 and 1. Okay, those would be the two cases together. So the probability of at most 1 is that X is going to now be less than or equal to 1, which is the probability that X equals 0 plus the probability that X equals 1. We're just using the table values, right? So the probability that X was equal to 0 is 0.3430 plus the probability that X equals 1 is 0.4410, straight from the table. And that's going to be equal to 0.7840. And what is the probability that all children have brown hair? So that is the probability that X equals 3. We're just taking that straight from the table, and that's 0.0270. So these are a bunch of things that we've already been able to work on from previous classes. All right, so let's take a look at another example. All right, a student guesses on every question on a test with 10 true-false questions. We're going to let X represent the number of questions they get right, and we want to use GeoGebra to find the probability that X equals 2, X is between 1 and 5 inclusive, and that X is less than or equal to 3. All right, so a couple of things to verify here is we are going to use GeoGebra when we are finding binomial probabilities. Okay, which means we need to verify probably that this is indeed a binomial situation. All right, so you can think of this as a tree, right? And that you have a test with 10 true-false questions, and we're going to have X represent the number of questions they get right. Okay, so I could have I could get the first question right or wrong. I had 2 chances to get it right or wrong, right? So it could either be true or it could be false. I've got 2 possibilities there. I've got 10 questions. That's my sample size. So my guess, if I'm just guessing, I have a 50% chance of getting it right, okay, for each of those questions. And I've got 10 questions total. So I know that N is going to be equal to 10 because that's how many questions I have. My sample size is 10. I have true, false, and if I'm guessing, that makes my probability of success equal to 0.5. And I only have 2 possible outcomes, right? I could either get the question correct or incorrect. So going through the checklist, I have a constant probability of success. So constant probability of success, P is equal to 0.5 because in each individual question case, I could either get it right or wrong, equally likely. And then I have a only 2 possible outcomes. 2 outcomes. I could either get the question correct or incorrect. Then I can check for independence. All right, so is this naturally independent or do I have pseudo-independence? And in this case, I'm going to assume natural independence because I'm not drawing from a fixed pool of questions. I mean, it probably does exist that way, but ultimately guessing one of the questions correct is not going to change my likelihood of guessing the next question correct, right? So I'm just going to say this is naturally independent. Okay, and then I've got my last thing to check is that I have a fixed sample size. So fixed n, which is equal to 10, which is the number of problems. So yes, it's binomial. Binomial, check. And that means I can define x to be equal to b. My sample size n is equal to 10. Probability of success is 0.5. All right, so this is my binomial distribution, and that's what I'm going to want to enter into GeoGebra. All right, so let's go ahead and get to GeoGebra. So I'm going to see if I can open this. I don't already have it open, do I? Okay, so let's go over here, and we're going to get GeoGebra. Okay, and we'll just go to classic. Actually, look for that one, GeoGebra classic. That's the one I want to go to. There we go. All right, now unlike our last case, right, and before when we were doing descriptive statistics, we were wanting to go to the spreadsheet to enter in our data. This time though, we're going to want to go to probability. So go to the probability picture. We'll just delete that old one. Okay, and now we're going to see this picture of a distribution, all this good stuff. Well, we're not dealing yet with the normal model, and that's what's being shown in the pull-down menu below the picture. So instead, we want to click on the pull-down menu and find binomial distribution. And that's going to come just after the dotted line. So the dotted line separates things that are considered continuous versus discrete. In our binomial distribution, we're doing whole number counts, right? Number of successes. That's considered discrete. So we're in the binomial, falls in that discrete category. So it's in the second half of the list. So there's binomial. Then you'll see beside it that it has these inputs for n and p, precisely the values that we have as parameters, or those inputs that are necessary for our distribution definition. Okay, so n in our case was equal to 10, so we'll enter that. And our probability of success p, that was equal to 0.5. So we'll return, and then we have this image here. Now what's cool here is over on the right hand side you can see a table, and the table over on the right hand side, so I'm selecting things on it right now, changing the highlighting, that is your probability distribution. So if I were to ask you to make this massive tree and add up all the probabilities for the different branches with the same number of correct questions, then you would create this very table. So that is also telling you the probabilities for the equal to cases. All right, so if I'm looking for the probability that x is equal to 2, I'm going to go to the table and look for where x is equal to 2. Let's see if I can get it just to 2. So that's going to be equal to 0.0439 from that right-hand side table, or the probability distribution itself. The next one I'm being asked for is the probability that x is between 1 and 5. So if I want between 1 and 5 inclusive, so there is the equal sign on there, I want 1, 2, 3, 4, and 5. So that's what I want. And notice that my histogram has shown the highlighted regions as well as the table showing the highlighted regions. Now I can do it that way, or a little easier is if you go down below where it says binomial, there's the less than, there's between, and there's greater than options. And I want to go to the between two things, and I want x to be between 1 and 5. So I'm basically setting up that same inequality that I had. I'm going to press enter just to make doubly sure. And the other way I can verify is that my formula that I have down at the bottom, the inequality, matches with what I want in terms of the right-hand table being highlighting 1, 2, 3, 4, and 5, and also matching with the highlighted bars in the histogram. So that means this probability is going to be equal to 0.6221. Okay, and the next one I'm being asked to find is the probability that x is less than or equal to 3. Okay, now notice I always have the less than equal to, greater than equal to's are going to be showing up here. And that's because we're using the same technology for all of those probability questions. And the technology itself is using the equals to case. So whenever we're setting these up, we're going to make them inclusive, so including that endpoint. So just keep that in mind when you're forming the binomial probability expressions. Always make it in terms of the equals to cases. So greater than equal to, less than equal to. All right, and we want less than or equal to 3. So I'm going to use the less than direction, but I want x to be less than or equal to not 5, but 3. Press enter or return just to make sure that the number changes. I verify that your picture is capturing those 3 regions, or 4 regions in this case, the 0, 1, 2, and 3, and that your table is as well. And that gives us 0.1719. Okay, so GeoGebra is going to make this process a heck of a lot easier than what we were doing before in terms of the tree to the table to the probability. And it allows us now to have sample sizes that are significantly larger than 2 or 3. So let's take a look at this next example. So there are 50 donors that come in to donate blood. It is known universally that 6% of donors have O negative type blood. And so we want to calculate the probability that exactly 2 of the 50 donors have O negative, 10 or less of the people of the 50 donors have O negative, 14 or more have O negative, and the first O negative person to walk in the door is the third person. So a few different question types there. All right. So again, we're going to assume in this case that we have a binomial distribution. A lot of the times you would be asked to verify this, but the only way we can calculate this is if we do assume that we have binomial, because we won't be able to make a tree of 50 branches, right? Those things get insane. So we're going to assume binomial, which means our variable x, the number of donors out of 50 who have O negative blood, is going to be distributed in a binomial way. And that we are having as inputs n, our sample size is the number of donors, which is 50, and the probability of success. So the probability that any one of those donors have O negative blood is 0.06. Okay. To say that it's binomial, we are assuming that we have a fixed probability of success equal to 0.06, that we have only 2 possibilities. Either they have O negative blood or they don't. Okay, so we're just looking at the complementary pairs here. We also want to make sure that we have independence or pseudo-independence. Well, in this case, we do have donors. We'd have, the sample is coming from a population that's of a fixed size in this case because they're people, but we're taking 50 out of a population of millions. Therefore, we're definitely less than 10%. Okay, so we would meet the pseudo-independence case there, and we have a fixed sample size of 50. So we do meet those conditions of a binomial distribution, which allows us to use these parameters and enter it into GeoGebra. All right, so now we want to find the probability that exactly 2 people out of the 50 have O negative blood. So we're looking for the probability that x is equal to 2. To find that, we're going to go back over to our probability in GeoGebra. Change this to 50 as our sample size, and then our probability of success, 0.06. Okay, now notice in doing that, our position of the histogram has switched over so that our expected number of, you can kind of see that balancing point, right? The expected number out of 50 who are going to be O negative is going to be kind of in that center of our distribution. So somewhere around, 3-ish, right? And then we can see from our probability distribution that's on the right, we have a whole lot of the situations where we're rounding effectively to 0. So from 12 on in our table, it's set to 0 because if we rounded to 4 decimal places, we would end up with 0. It doesn't mean there's absolutely no chance of this happening, but the probability rounded to 4 places is equal to 0. And so we're not, with 6% chance of O negative blood, going to have a situation likely to come up where we have more than 12 out of those 50 who have O negative. It just isn't reasonable. But the 2, having 2, is going to come from that same table on the right, and that's 0.2262, or about a 23% chance of having exactly 2 out of the 50 donors have O negative blood. Okay, next one, probability that we have 10 or less. So X is less than or equal to 10. Okay, we could try adding those all up, but it is easier to do the less than direction. X is going to be less than or equal to 10. Okay, and then we're going to press enter, actually, just to make absolutely sure. And then we look at the probability to the right, and that is, 0.9998. Now that's really close to 1. It's not exactly equal to 1. So we're just going to leave it with the 0.9998 form until we, unless we got to the point where it was going to round to 4 decimal places, going to the 0 and a 1 in front. We don't need to worry about changing anything. Just take the output that GeoGebra gives you. All right. And we know that this is going to be correct because if we look at the picture, we have shaded almost everything in it. Okay, so almost that entire curve has been shaded. If we look at the right-hand table, there is only that 0.0001 that has not been highlighted in our table, and then the rest were zeros, right? And so that makes sense that we have almost 100% chance of having 10 or fewer people out of our group of 50 who have O negative blood. All right, so 14 or more have O negative blood. Well, we should be able to look at this right away and go, okay, well, 14, there's a 0% chance listed on our table, and everything greater than that is also listed as a 0. So in that case, we're going to say the probability that X is greater than or equal to 14 is actually going to be equal to 0, but rather than saying flat out 0, meaning no chance of this ever happening whatsoever, we want to give it a little plus sign above it. Okay, and that means there's a slightly more than 0% chance. 0%, 1%, 0% chance and 100% chance, 0 and 1 for our probabilities. Those are extremes that are used pretty much only when we are dealing with the rules of probability as opposed to actual probabilities that we calculate. So we want to distinguish that from the extreme will never happen case, and that's what we do is we put that little plus sign on there. If we had the opposite situation, so let's say we rounded to 1.0, then we would say that that was a 1 minus is what we would label it as. So that would be just less than 100% chance. Same as this means slightly more than 0% chance. Okay. All right. And then the last question we're being asked is, what is the probability that the first O negative person is the third person who walks in? And so this is a slightly different type of question. This is actually referred to as a geometric distribution, but rather than worrying about learning a whole different distribution type, we can just kind of reason about this. So the probability, and this doesn't have a special relationship to our variable X, so we'll just write it out. So the first O negative is the third. I can't spell today. Third. Here we go. It's the third person. And that means that the first person who came in was not O negative. Okay. And if we know that there is a 6% chance of being O negative, what is the probability of being not O negative? Well, that's going to be 94% chance, right? So 0.94 for the first person. And then the next person has to also not be O negative, so another 0.94. And then the third person must be O negative. So that's when we would have 0.06 afterwards. And so we take the product of all of those. It's going to be 0.0530. Okay. And we don't need to worry about the rest of the people. It actually turns out that it's a whole bunch of series of ors, so sums and things that are happening afterwards. And it does not change the actual calculation of this to leave it at this endpoint versus branching all off and looking at all the other outcomes. So we can just stop when we meet that condition of the first person to have whatever characteristic we are looking at. Okay. So the next thing we want to talk about here is the binomial expected value and variance. So I mentioned when we look at the histogram in GeoGebra, we can get a sense of what is the most likely outcome, and then that is going to signal what our expected outcome is, right? We are expecting that because it is the most likely to occur. And it actually turns out the probability or the calculation of that expected value is pretty easy now. So if we have a binomial distribution, our calculation for the expected value is just equal to NP. So N being that number of trials or sample size. So sample size times the probability of success. And then our standard deviation is going to be equal to the square root of the sample size times the probability of success times the probability of failure. Now, what you want to notice here is how that compared with our Bernoulli calculations. Remember, we said that Bernoulli, when we had a sample size of 1, so Bernoulli, N was equal to 1. And we said that E of X for Bernoulli was equal just to P. Well, now to get to binomial, N is greater than 1, and E of X is just multiplied by N compared to the Bernoulli, so it's NP. Same as for the standard deviation. Bernoulli, right? The standard deviation of X was the square root of NP, or sorry, of PQ. And now with the binomial, we're just taking that and we're going to have the standard deviation of X is equal to the square root of NPQ. So we're just multiplying by N, increasing our N from 1 to something greater than 1. So again, that extension from Bernoulli to binomial is just the number of trials that we're running through, which is pretty cool. Okay, so let's take a look at those 50 people donating blood again, and let's find out the expected value and standard deviation. So E of X, the expected value, how many people out of those 50 we expect to have O negative blood, is going to be the sample size, or number of people, 50, times the probability of success, or P, which was 0.06. So 50 times 0.06, that's equal to 3 people with O negative blood is what we expect. Okay, and the standard deviation of X is going to be the square root of NPQ. So sample size times the probability of success times the probability of failure. Okay, remembering that Q is equal to 1 minus P. So this is the square root of NPQ, and Q equals 1 minus P. All right, and then we run through that calculation, and we're going to get 1.68 people, or rounded to 1 decimal place, we can do 1.7 people with O negative blood out of the 50. Now you're going to see in GeoGebra that it tells you that as well. Okay, so up on the top right underneath where it says distribution, above the peaks, you'll see mu equals 3 and sigma equals 1.6793. Okay, that is your mean and standard deviation for the distribution. Now, unfortunately, I do still need to see your full calculation. So I would need to see these shown for your work to get to those numbers, but you can always verify that you did the right calculations by looking at GeoGebra just above the diagram. It'll show you those numbers. Okay, z-score for X equals 8 people. So we want to find how far or how many standard deviations having 8 people with O negative blood, how many standard deviations away from the expected value is that? All right, so Z is going to be equal to our data value, which is how many people we're looking at. X is equal to 8 minus the mean, which is the expected value, so minus 3, divided by the standard deviation, which is 1.7. Remember to do the calculation in the numerator first entirely, and then divide by the standard deviation. So that's 8 minus 3 equals, then divide by 1.7, and that is going to be 2.94 rounded to 2 places. So always round z-scores to 2 places. And the other thing to remember is these are no units. This is number of standard deviations from the mean, or in this case, expected value. Now, when we have a z-score that is greater than 2 standard deviations from the mean, so either greater than positive 2, less than negative 2, that means we have an unusual outcome. So yes, this would be unusual since it is more than 2 standard deviations from the mean. Okay. All right, so let's take another look at an example. So in a game of chance, there's a 15% chance of winning a prize. You play the game 20 times. If we let x equal or be the number of times you win, is x binomial? All right, so we need to run through all of our conditions. So the first thing, remember, is we need to verify that we have a fixed or constant probability of success. So constant probability of success, which we name P, and that's that 15% as a decimal, so P equals 0.15. Do we have just 2 outcomes? So only 2 outcomes. Yep, we could either win or not win. And these are pretty much always phrased in terms of complements. So you have one characteristic that you're interested in, and everything else is its complement to that. The other thing that we need to check is we need to check for independence. So are the games independent from one another? In this case, again, we're going to assume independence. We don't know of a fixed population that's being selected from here, but our chance of winning is not going to be changed, presumably by winning one game from one to the next. So naturally independent. And then the last thing we need to check is the fixed sample size. So n is equal to 20, so fixed sample size. And so long as we meet those 4 conditions, we can say yes, it is binomial. All right, remembering again, it's likely going to be in here already, but we're also looking for the number of successes in n trials, because that's the main phrasing. So is x representing the number of successes in n trials? So yes, that is the phrasing here as well. Okay, so if x is binomial, which it is, we want to define the model. So we start by giving the name of the variable that's being described by the model. So the variable is x, and it is in fact binomial. So we use the letter B to describe that or define that or to state that distribution type. And then the parameters, or the things that we require to input to calculate or do any probability calculations on this distribution, are the number of the sample size, or the number of trials, which is 20, and we also need the probability of success. So that was 0.15. Okay, so that is defining the model. What are the expected value and standard deviation of x? Well, we know that it is binomial, so we just need to calculate E of x, which was NP, which is going to be 20 times 0.15, and that is going to be equal to 3. And these are wins that we're expecting out of our 20 tries at the game. And the standard deviation is going to be equal to the square root of NPQ. So 20 times 0.15 times 0.85, Q being the probability of failure, 1 minus the probability of success. Okay, and then that is going to come to 1.6 to 1 decimal place, and these are also in terms of our variable, which was wins. Okay, what do the expected value and standard deviation tell you? That tells us that we can expect to win 3 of the 20 games, give or take, or take 1.6 wins. And again, this is long run relative frequency. So if I were to go in and play this game over and over and over and over again, I'm doing groups of 20 plays at a time, I would say, well, maybe out of one group of 20, I won 4 times, and another time I won 3 times, and another time I won 2 times. And so that's what I'm averaging over the long run. Okay, and would winning 7 times be unusual? So unusual means we need to calculate a z-score. Z-scores require that we have a mean and a standard deviation. For our random variables, the expected value and standard deviation are exactly that. All right, so we're going to do z is equal to our data value, which is what we're checking the likelihood basically of, right? So that's at 7 times, so 7 minus the expected value, which is our mean, so minus 3, divided by our standard deviation, which was 1.6, making sure we do that calculation in the numerator first. So 7 minus 3 is equal to 4, divided by 1.6 is 2.5. 2.5 is greater than 2 standard deviations from the mean. Therefore, this time winning 7 times would be unusual. So yes, winning 7 times would be unusual. Okay, and again, because our z-score is greater than 2, meaning more than 2 standard deviations from the mean. What is the probability of winning 5 times? Okay, so that's exactly 5 times. So I'm looking for the probability that x equals 5. And I don't want to have to do a tree of 20 things. I know I have a binomial distribution. I checked my 4 conditions. So I can go to GeoGebra. So I'm going to enter in my sample size. Okay, and in this case, I'm looking back up over at how I defined my model at number 2. And that's what I'm going to be entering is the 20 for n. And then my probability of success was 15%, so 0.15. Okay, and I am looking for the equals case, so I go to the table on the right, and I'm checking just for where, let me see, I'm trying to get this down to just the 5. Well, I'm looking for the 5. And I cannot seem to get this to just go to 1 point, but it's the 0.1028. So equals, so equals 0.1028 is the equals to 5. All right, what is the probability of winning at least 5 times? So at least 5 would be 5, 6, 7, 8. So the probability that x is greater than or equal to 5 is what we're looking for that. And I can try and shade this so that I'm getting just greater than, but I think it'll be easier for me to use the controls under the binomial sign to do the inequality. So I want at least is greater than, and I want at least 5, and then I'll do enter just to make sure. Then I check my table to the right to see that it's shading 5 or more. The picture shades 5 or more. That's all looking good. So then this probability is 0.1702, so about a 17% chance of having winning at least 5 times out of those 20 plays. And what is the probability of winning no more than twice? So no more than 2 times, so not 3 times, not 4 times, not anything greater than that. So that means I'm looking for less than. So x is less than or equal to 2. Okay, go back to my less than symbol. less than equal to 2. Okay, and double check with enter. Okay, check my table, check my shading. Those look like they're representing the same number that I'm wanting there. And the direction of the inequality is what I wanted there. So that'll be 0.4049. So about a 40% chance of getting no more than 2 wins out of those 20 games. What is the probability of winning 2 or more? So probability that x is greater than or equal to 2. Okay, so I want greater than. X is greater than or equal to 2 is already typed in. I can see the shading on the right. I can see the picture shading it appropriately to the greater than direction. So that is going to be 0.8244. And what is the probability of winning 12 or fewer times? 12 or fewer, probability that x is less than or equal to 12. So we want less than or equal to, and change that to 12. Whoops. Enter. Okay, got my picture all lined up, and notice that in GeoGebra it says 1. So we put that down, but we also want to put in that minus to mean just ever so slightly less than once, because to say 1 means there is an absolute 100% chance that this is going to happen. And that's not necessarily true. It is possible, though incredibly unlikely, that we could win 13, 14, 15, 16 times. Okay. All right. So that is the basics of the binomial distribution. So binomial distribution means we're asking a question about the number of successes in a fixed number of trials. We can verify that a scenario is binomial by checking our 4 conditions: constant probability of success, just 2 possible outcomes, a success and a failure. You're going to have independence naturally or pseudo-independence, meaning our sample size is less than 10% of our population. And we also need to have a fixed number of trials or samples being drawn from our population. Then once we know we have binomial, we can define it to be the variable name equal to b with n and p as its parameters, or things that are necessary to pursue any other calculations with it. We also know the expected value and the standard deviation. They're nice and easy to calculate for this type of random variable. We do not have to do those big old formulas. We can just go ahead and do the calculation for expected value as NP, and the standard deviation is the square root of NPQ. Nice and easy there. And then once we have that, we can go to GeoGebra and we can do all the probability calculations in here. Please don't try and do them by hand with big trees. It'll get way out of control. And we can also check for unusualness from our z-score, since we have our expected value and standard deviation. So those are the main things that we will be looking at for binomial distributions, or at least up to this point. And you can stay tuned for a little more stuff happening with normal models coming up next.